voltage for VT accurately, now the current will be fed into your protection relay. Okay, the relay, the brain, which will decide whether you are facing a condition of fault or not. So there are various configuration, uh, overcurrent protection, distance protection, and everything. So our focus now is on the overcurrent protection, usually used to protect a feeder, okay, distribution feeder coming from the distribution in your substation towards your own load. Okay, this is done by uh, the IDMT relay, overcurrent relay, right? So overcurrent protection, as the name implies, is basically an protection against current. Okay, normally referred to fault current. Overload might have might be considered as a fault as well, but it's normally deal with differently, because let's say your rated value of your conductor is 100 amp, you might be overloading it to be 120 amp, a little bit overloaded. That's not a faulty condition. It's coming from your load. Okay, you use more load, then of course it's overload. But fault current is different. Fault current is going to be way more than that. It's going to be maybe 1000, 2000 amp, 20 times the rated current. So it is the focus is basically on the overcurrent due to a fault. Okay, it falls under non-unit protection categories, and so if it is non-unit protection, you might see some overlapping of boundaries of two or more protection system. So when there's an overlapping, you need to do some coordination. All right, let's move on. This is a drawing of a feeder with 1, 2, 3, 4 sections here. This is the generation sites towards the end, ujung kampung di sini. It connects to your load. Now, when there is a fault here, the fault current, let's say 1000 ampere. So the fault current will be coming from this supply side, goes to the fault point here, right? So you are putting a CT at this section, this section, this section, and this. So basically 4 relays. Okay, this relay, 51 relay, is able to detect the fault current. Okay, if this relay are to trip, send signal to the circuit breaker, this part will be isolated. Circuit breaker akan buka, this part is isolated. Okay, but also, since that 1000 amp is seen by this relay as well, and judged to be the fault current, the relay will send trip signal to the circuit breaker will open, this part will be affected as well. Okay, this part. And kalau ada lagi kat sini, another branch, those will be affected as well. So basically, with similar relays here, fault at this point will cause this breaker to open, this breaker to open, this open, this open. Basically, the whole feeder will be affected. So we don't want that. So what do we do about it? Right? So this is what is called discrimination by time, where you put on a delay to each relay. Okay? So the relay that is closer to the source will have longer operating time. It detects the fault 1000 amp, but it takes 1.45 seconds to react. But the one that is closer to this, to the fault, takes faster time to operate. So by doing so, okay, let's say there's a fault there. After 0.25 seconds, this part is isolated. there'll be no more fault. So the current 1000 amp fault current is not seen by the relay anymore. So before 1.45. So this relay does not trip. Relay D does not trip. Okay, so comprise a definite time delay of the current relay. Going to the source side, the delay is increased. Okay, but the problem with this is that when you have fault occurring here, the fault current instead of 1000 will be maybe more, maybe 3000. The closer to the source, the larger the fault current. Because if you were to draw this equivalent circuit of this, you have a source there, source impedance, and then section B's impedance, section C's impedance, and so on. So the fault location determines the amount of current. The closer to the source, the lower the impedance. I fault equal to E divided by Z total. We have smaller impedance here. So for smaller impedance, will give you higher current, but the problem with that is that you are reacting slowly for high fault current. This is more critical, can brings more harm, more damage to the equipment, but you are very slow. But this relay, this fault current is seeing 1000 amp only, but it acts very fast. Macam overreact, right? So that's the problem. Not only you need time to coordinate them, but the clearing time, the time should be, should consider the amount of fault current. All right. So discrimination by time, kind of okay, but not so okay. We can discriminate by current, no problem. So in this case, you have a fault at point 2 here, F2. The fault current would be the voltage 11 kV divided by total impedance here, the source impedance 0.24 and 0.27. It is 6400 amp. Okay, you set your relay to trip if the current is greater than this, right? To protect section B and C. So the relay is here, right? Fault current is 6400 will trip. This relay will also see 6400, but it is being set at a different value. Say it is set according to the fault within its section only. Okay, fault at F1 will produce fault current is which is 8800 ampere. So your setting is 8800. The fault current at this equation F2 is lower than that, so this does not trip. Okay, so fault current within this area, the blue one, shall not cause this relay to trip because the relay setting is 8800, whereas the fault current here is going to be this. Here comes the problem. Now, fault at this location, right, F3, should be dealt with by this breaker, right? Because it is within this section. But the fault current here might be 8700. Of course, you have up 48524 and just a little bit impedance here. So you're going to have some sort of similar value here, close to this. Numerically, you can distinguish this thing, but remember that you will have a CT with certain amount of error. Let's say this class 10P. When the error is plus minus 10%. So the error should be whatever 880 plus 880 minus 880. So 8700 might falls under this within the range of the CT. So in that case, this relays here sees an external fault with a value that is greater than its setting. So we trick here. So the problem is you cannot distinguish fault at these two locations. The basically, essentially, effectively the same point, two different side of the bus bar. Okay, sorry, bus bar, the conductor here. You have a fault here. You have fault here. Different side only. So not very practical for you uh, to distinguish those fault. So again, you're screwed here. Okay, not so good. Discrimination by time is not that good. Discrimination by current is not that good. So how about discrimination by both time and current? Might be better, but with certain limitation. We'll deal with the limitation later, but for this time, I'll just show you the uh, advantage of having this discrimination by both time and current. For you to do so, you need to have a certain characteristic of the relay. Okay, the relay needs to have an inverse relationship. Okay, the operation time is inversely proportional to the fault current. As opposed to this operation time can be instantaneous, right? And for this discrimination by time, the operation time is fixed at whatever fault values. So in this case, you have a characteristic that is inverse shown by this red line here, right? So fault current of a certain value here, this is the operating time. With low fault current, a smaller operating time. Okay. Okay, you have let's discuss this first. Okay. Uh, for fault at location one, F1, the fault current will be lower. Let's say it is 500 amp. So fault closer to the source here, F2, will provide a larger fault current, 1000 amp. Okay, so when fault occurs at this particular point here, F1, you would want to set your relay to trip at this value, 0.5 second, right? Settles. So you need a discrimination with relay A because this relay A will also see 500 amp. Okay, but for relay A, you will adjust it to operate at 1 amp. Sorry, 1 second. For fault of 500 amp, the relay B will act faster because it is closer to the fault, and relay A will be slower here because it's closer to the source. So you have a discrimination by time here. Now, what if there's only fault at F2? Fault at F2 will provide a 1000 amp current here, but you have fixed this point here. So basically the curve A remains the same, does not change. But with this curve, the 1000 amp will give an operating time of 0.6 second. So it is faster as compared to this. So you have this characteristic that is faster with high current and slower with lower current. But if you notice, this relationship is just for relay A. Okay, for relay A, the higher the current, I mean, also relay B. But if you were to compare these two, not necessarily so. Why? Because you see 1000 amp here, it takes relay A to operate at 0.5 slow, but 500 is 0.5 fast. So if you compare these two relay, so that the principle of having faster tripping time for higher current does not hold anymore. But of course, if you want to adjust it, sure, no problem. We have 500 gain here, 1000, right? So this one is kind of fixed. You want 1000 to be faster, you can imagine that you want it to be 0.3 second here, fine. So that red curve needs to be moved down. You're going to have this somewhere in between. So in this case, so 1000 is 0.3, 500 is 0.5. That holds. But the problem with this is that you're going to have a limited difference here. So this is very important. We'll cover this later because the distance between this and this must be maintained above a certain value. Okay, this must be greater of how many seconds. So that's the problem. Okay, so you need to balance up whether you want to have a fast operating time or sufficient time delay between those relay characteristics. Okay, so we'll deal with this later on with the time delay, discrimination time. Let's focus on this curve. This curve is basically defined by standards. It's not simply, you can simply draw an inverse curve here, maybe another curve with a lower slope. Maybe this is less steep. It's not you cannot simply do that because this slope has been defined by standard. Okay, you see, you have standard inverse where the slope is the blue one. The steeper is very inverse and extremely inverse. So these are defined by IEC or even IEEE. You can Google that different characteristic. Of course, IEC and IEEE will have a different equation for that. Okay, the relationship for standard inverse is basically the operating time. The operating time, relay operating time is simply 0.14 over fault current divided by the relay setting current to the power of 0.02 minus 1. So this is the equation for IEC. For very inverse, you have different equation. ROT is equal to something. But unless IEC and IEEE will have a similar, not so, they're very close if you're talking about standard inverse. Standard inverse, IEC and IEEE are kind of very close. The same goes to very inverse, IEC, and IEEE will be very close. Okay, so that is inverse relay. So you have instantaneous relay yang trip instantaneously. You have definite time. This is not inverse. Definite time is this one, the red one. Meaning to say, regardless of the value of the current, once it detects the fault, it will trip at 1 second in this case. You can set it to be maybe 0.5, but your setting is of a definite or fixed time. Now, what is IDMT? We discussed about inverse characteristic, but this inverse characteristic is not continuous to whatever higher current. It has limit. Up to this point, it will not go any faster. It will stay at the definite minimum time. So that's why it's being called IDMT. You have inverse part here and a definite minimum time. So there are two things here. First, the inverse part can be adjusted, whether it is standard inverse, very inverse, and semi inverse, and it have a definite part, which also can be adjusted. Okay, so the curve will be inverse and definite time. Right? I guess as for the characteristic, you're clear. This is coming from the equation given, by IEEE IAC and so on. This is the case for our current technologies. So the relay is basically a microprocessor, a microcomputer. So it receives current from the CT, it goes to some sort of conversion, analog to digital converter, and so on, some sort of processing, signal processing. And from there, it will compute the operating time, right? Operating time, software based. But previously, with electromechanical relay, so the curve is actually based on the physical structure of the relay. The relay is consist of a core, a disk, and everything. Nanti saya bawa lah sampel. Awak boleh Google electromechanical overcurrent relay, macam mana bentuk dia. So the physical size of this disk will determine the characteristic. Some sort, and then some core is there, materials being used, and so on will determine the characteristic. So basically, for one particular uh, relay, physical relay, whole relay, electromechanical relay, you have a fixed size of this, fixed material and dimension of the core and so on. So you have a fixed value of curve for that. And then you'll design a different relay for very inverse with different dimension and so on. So that used to be the case. But these days, it is software based. One microprocessor, you can simply select whether it's going to operate in this mode, standard inverse mode, or very inverse mode, and so on. So everything is built in. Okay, you just change the setting. Previously, if you're using electromechanical based relay, if you want to change the characteristic, you need to remove the relay and change with different relay with certain characteristics that are required. Okay, I guess it's time for us to stop. The next class will focus more on the settings that is available for this overcurrent relay. Okay, thank you very much. I'll be sharing you the attendance. Yeah. Boleh lambat sikit. Tak buat lagi ni. Okay, I'll just take the attendance from this Webex punya screen. Okay, tak apalah. Saya dah ambil attendance on Webex. Class dismissed. We'll meet again next week. Thank you very much.
Thank you, Doctor. Thank you, Doctor. Thank you.